This talk is about physical destruction of data storage units. And the background of this talk, and sort of why I decided to do it, is thinking about the security risk of the waste stream. So we're, most of the people in this room, this conference is not one of those conferences where there's like a lot of kids here, a lot of young people. We are old school. We remember the old days where we would go in the waste stream, go trashing, and pick stuff up and find out information that way. And the waste stream, if you're not careful about what you throw away, you can lose secrets that you would rather keep from your competitors if you're a business, from criminal organizations, or just from the general public. Sometimes stuff is embarrassing if people know it. And the way that this stuff happened in the old school, I don't know how many people in this room did it, but we used to go crawling around telco trash cans, for example, to get phone system manuals. That's how we found out how things worked. But the amount of data that can be easily, accidentally thrown away is getting bigger and bigger. So we're not just looking for printouts anymore. We can get a thing that we can get from a junk store or whatever that has terabytes of potentially sensitive data on it. So for example, I'm sure a lot of people here are familiar with a paper that was put out where people went out and they bought a ton of old printers and copiers. And they pulled the hard disks out of these modern printers and copiers because they're basically big scanners these days. And they don't do necessarily secure erasure of what's been printed or what's been copied. And they were able to recover, this is a United States paper, so they were able to recover a lot of sensitive data like social security numbers, tax information, because people photocopy their tax returns. Another interesting example is if you've got a mobile thing, like maybe a drone, some kind of robot, and it's got sensitive information in its data storage device. It's out there in the world. It can crash. Someone can recover that thing and potentially get useful stuff from it. So you want to be able to destroy that thing. And in particular, the motivation for this talk, what if someone tries to take your thing while you're still using it, right? They take your laptop, they raid your data center in particular. So we would like to be able to destroy vast quantities of data when we don't have time to perform a secure erase. So our goal in this work is to flip a switch and make these data storage devices go away. No bits left standing. You might say, hey, well, what about crypto, right? We're all into crypto. It's great. We should use it. It's not always going to solve everything because crypto is only as secure as the key. And it's very common for keys to be unexpectedly available and recoverable from storage media. Like keys tend to be stored somewhere, especially in hardware crypto systems, and you might be able to recover them if that thing is still physically available to be messed with and hacked. Talk to any of the hardware hacking guys. And we also want a solution that's data center scale, right? So we can have racks and racks and racks and racks of hard disks, and we can kill them all. And we're assuming that our adversary has high capability, right? A criminal adversary such as a state intelligence agency, for example, or such as a well-funded foreign criminal organization. So let's just really do this properly. So for reference, let's take a look at what they do industrially to get rid of data. If you want to decommission your disks in a way that's going to satisfy your business requirements, a pretty standard thing to do is to magnetically degauss them if it's magnetic storage media, and then use a machine like this, an industrial shredder. You can shred things in this. I've seen people shred a torpedo in one of these things. They're pretty crazy. You see them just tossing the drives in and bang. But you have to predict your adversary here. And as I said, a highly funded forensic organization are able to collect and exploit physically destroyed hard disks. So if you want to really nuke your data from orbit, you do those two things. You degauss, you crush and shred, and then you also burn. I know this because I had conversations in the course of doing this work with United States Marines who are attached to UN MOVIC, the weapons inspection group, weapons of mass destruction inspection group in Iraq, and they were under instructions from their relevant three-letter agencies that if they found any data storage device, no matter its physical state, if it had been crushed, if it had been shredded, they would collect that because data could still be exploited unless it had also been burned. So here's my rules that I'm trying to keep to in this research here. We have a 1U server holding our disks. We're allowed to have 1U above and below it for whatever we want, right? So it could be protection, could be concrete, to make sure that we keep our destruction inside this thing. Could be hot gas extraction if we're doing thermal methods. 60 seconds to completion. So these guys, your Russian mafia busts into your data center, you flip your switch, they're not going to be able to get anything in 60 seconds out of your racks. So that's what you've got. We don't want to set up our fire systems. We don't want to have sprinklers going nuts. We don't want to destroy all our other valuable equipment. We just want to destroy the data. Same thing with the damage. We want to contain that with within our data storage equipment. We don't want to destroy all our computers and other things. We also don't want to destroy our people who are sitting there, like looking after the colo facility or whatever, so we've got to keep them safe too. Quick word on the kind of technology that we're dealing with here, our hard disk technology. Most large-scale data storage still takes place on spinning platters, right? So you've got your circular things, they spin. The circular things are still mostly made out of aluminum. But more and more frequently these days, for reasons of uniformity of manufacture and high speeds of rotation, they're being made out of glass. So in my destruction work here, I'm going to concentrate on aluminum platters, because anything you can do to destroy an aluminum platter will also work on glass. The coating, so how you've got this like circular lump of aluminum, what it's coated with so it actually stores data. You have some underlayers, that typically cobalt, nickel, iron. The magnetic stuff is typically stored with cobalt, chromium, and platinum. There's actually platinum in hard disks, so like most electronics, there's valuable metals in them that you can recover on an industrial scale. And then these layers are separated with very, very thin layers of ruthenium, 4 atoms thick. And this is the reason why chemical attacks I'm not investigating in this work, because the actual platter material of a hard disk is very chemically resistant. Okay, it's going to be very, very tough to do a chemical attack on this inside the 60-second time frame. And also a little bit of looking at solid-state drives. So right now, industrially, we're not using solid-state drives for everything, but they're more and more common. Almost everyone's laptop now has an SSD in them. And SSDs are just computer chips on a circuit board. So you can do whatever destructive methods will work on a computer chip, you can do for solid-state drives. And we'll take a look at this towards the end of this presentation. So I'm going to concentrate on 3 areas of attack. Number 1, thermal. Then kinetic attacks, so that's anything that physically mutilates the drive. And then finally, electric attacks. So first in thermal, our goal in a thermal attack on a hard disk is to exceed the Curie point of the magnetic media. Okay? So that's the point at which these organized atoms, so they're magnetically organized, we can read that data back, they become disorganized. We can no longer recover that magnetic information. For cobalt, the Curie point is around 1115 degrees Celsius. So to put that in perspective for you, if you were to pour a bronze sculpture out of tin bronze, the temperature at which you would pour that bronze is 1050 degrees Celsius. So this is above a bronze pouring temperature. It's very hot. So here are some ideas that I looked at but won't present, or I didn't bother to look at. Anything involving gaseous flame torches. You can get to that temperature with them, but it takes a long time, especially because a hard disk is a giant slug of aluminum in the base case. It's a huge heat sink. It's tough to get the platters that hot in a short time. I really wanted to look at flameless chemical reactions, just mix 2 things and have it just get really, really hot. I couldn't find a good mix reaction that wasn't hypergolic, which meaning catching fire, that would get to the temperatures that I needed. I don't look at ovens because they're boring. We know we can reach that temperature. The speed, is a little tricky in 60 seconds, but it's just not fun to do. We just know we can do it. Similarly, inductive heating and melting. So if you're in a foundry, you're melting bronze to make a sculpture, you're going to use an inductive furnace most likely, unless you're doing a really big sculpture. So that use an oscillating magnetic field to melt your metal. It'll definitely work, and it'll have the benefit of degaussing the drive, so it's not interesting to research. We know it can work. But the cabinet to do an inductive heater is huge, right? It would probably violate our space requirement. So here's the very first thermal attack that I tried when I first started this, a plasma cutter. So you can buy one of these very cheaply from a hardware store. Produces a jet of very high temperature plasma. You can cut anything with it, cut solid steel. And this turns out to be a super nice method. 40 seconds to achieve full penetration of the drive. As you can see, it's not creating a huge mess, and it gives you a nice little spurt out the end when it's done. You can see when it gets through at the bottom there. There it goes. Yes. Few little blobs come out. So totally wins on time. Let's take a look how it looks like inside. By the way, drives are a big heat sink. That means they absorb heat. This drive stayed hot for a very, very long time. So this shot is after I repeatedly burned myself taking the screws out. And we can see that the drive was spinning, but it stopped spinning pretty quickly. We haven't fully gone around the disk. Basically, it had heated up, the spindle had seized, and we stopped spinning. So that's an interesting thing. Here's a close-up. We can see we've done some damage to the surface of the drive here. Much more damage, by the way, than you would do in this amount of time with a flame torch. And as we take the platters off, we can see we've gone all the way through them. So this method, totally feasible. But what we would need is a little array of plasma nozzles that goes around the circular drive because we can't rely on that drive to stay spinning. So that's great. First success, right off the bat. Next, I thought, well, the flame torches don't work too well, but the aluminum in the platters themselves is a fuel, as long as we can just get it to burn, right? What makes things burn? Oxygen. So if we pump oxygen into the drive, so we could make, obviously this is a test rig, but we could make an injector with a pointy nozzle on a little hydraulic actuator that punches through the drive when we need it to and just floods the drive with oxygen. We just need to get it going. So here, I've punctured a drive, I've put in a little starter, and we're going to pump oxygen through, get it going, and see how much of those platters we can get to burn. Are we playing? Oh, sorry, all right. These video files are huge, so they don't always tell me when they're playing. 3, 2, 1. So this is just a little short circuit going on that input cable, and we can see that oxygen is really helping things go. And really the only thing that stops this from burning indefinitely is my plastic oxygen hose melts, and we start to get a little worried that it's going to get out of control, so I shut the oxygen off. Here is some high-speed footage of that, just for fun, so that we can see the progression of getting this thing going. And what that shows us there is it actually burns through the top plate of the drive very, very quickly. Oxygen is fun stuff to play with. All right. So, surveying the damage. Again, we've totally burned through this aluminum top case of the drive. We open it up. We can see we've done some damage there. Clean off the drive, and we can see that some amount of that normally very chemically resistive platter, in that short time we were pumping oxygen through it, has fully combusted and melted down. So again, this is a technique that is potentially feasible with some engineering effort to make sure that we get all sides of the drive and we keep our oxygen pumping in for long enough that we can do this, for our minute. But moving on now to what when I told people I was going to do this research, everyone says to me, "Oh, that's easy, thermite," right? I'm like, okay, well, that's great. The military uses this stuff in incendiary grenades to cause very high temperatures and destroy stuff. So we know that it's a thing that is used to destroy stuff. What I was mostly interested when I first started was to see if I could make a thermite slurry, right? So I could make this in a form that's not a powder and it's not like a compressed block that could be injected and pumped into the drive by some physical hydraulic injection mechanism. These efforts failed. I spent a lot of time on the slurry, and I don't have time here to go through all of that. Just suffice to say that the slurrifying agents, and I tried a lot of them, prevented the thermite reaction from occurring. What is the thermite reaction? Many people played with this when we were in high school or whatever. It's simple aluminum, powdered aluminum, and powdered iron oxide or rust. These two metals, they just swap their oxygen partners, like they're at a kind of a swingers party, and the aluminum takes the oxygen home, has some fun with it, and the iron becomes molten iron because this reaction releases a lot of thermal energy. It reaches a maximum temperature of about 2,500 Celsius, so more than what we need to hit our Curie point. If you want to try this at home, very easy to make, 3-to-1 iron oxide to aluminum by weight. The grades of the chemicals, obviously finer powders, it'll go faster, but you can use anything. You can actually scrape rust off an old fence and do this. It's great. So the slurry didn't work. So I thought, well, what if we you know, if we're like a really serious organization that wants to protect our stuff, what about if we modify our hard disks ahead of time and we pre-insert the Thermite? Because 5¼ drives do have a fair bit of free space in them. You don't need the space here behind the read heads. They don't need to go into that space. So I rigged up, there's a couple of extra pins that aren't used on the bus, so I rigged them up with a little igniter so that you can just apply power to one of these unused pins. Put a little bag of Thermite inside there. Drive still works after you do this. 15 grams fits in there, which, by the way, I just really enjoy doing this stuff because I get such a kick when I go through the airport or whatever and they make me turn some electronics on as though that means that it hasn't been tampered with, right? Sorry, guys, I can put all kinds of destructive stuff in electronics and still have it work. So let's see how 15 grams does here. 3, 2, 1. So, looks great from the outside, right? There's some flame, but we can totally deal with that inside our rack mount unit. Let's take a look at the damage. We can see a big blob there from that molten iron that's been produced. But I don't really like what I'm seeing here, right? Because everything's still concentrated where that bag was. The platters look okay. Here we go, doing some forensic wiping off. Very, 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 very high-level forensics, just to sort of see how those platters look. And yeah, the platters look okay, right? This sucks. And sure enough, after we wash it off, we can see basically nothing has happened to these platters. It's survived a pretty high temperature reaction going on inside a closed case there, with really no damage at all. I'm pretty sure that the government is going to be happy to forensically analyze this disk, so that's a fail. But actually, if you look at military thermite grenades, they don't use straight thermite. They use what's called Thermate. Thermate is 70% thermite plus 30% barium nitrate, and the barium nitrate actually increases the burning temperature and it produces gas, so it spreads everything around. And that looks like what we want there, right, in that pre-insertion, because now we're going to move all that stuff across onto the platter. So let's take a look at a little Thermate experiment here. You can see right away how much more there was stuff trying to get out of that drive, right? Here's a high-speed shot of it. Yeah. So I don't remember the frame rate of this shot, but it's probably like 2,000 frames per second, something like that. Not super high speed. We'll go faster later on in this presentation. But yeah, there's a lot of material getting ejected from this drive right now. So things are really moving in there, and they look pretty hot. A lot more sparks and debris than the plasma cutter, you recall, right? So we're going to have to deal with our fire suppression a little more if this method works. Still going here, you know. Things go for a long time at when you're filming in high speed. Nice thing to have in the background at parties, though. If you have like a projector, you can just stick that on there. This kind of stuff. Here we go, opening up the case afterwards. I'm getting more intelligent with this project and using gloves now. Actually, that's not me. That's my friend Miles Sledlip. This was done in his workshop, and we can see already that things have like we're doing better here.
Quite impressive compared to.
I'm impressed.
Thermite. I guess there's a reason why the military uses this formula.
So here we go, close-up shot. You can see all these little balls. That's iron, elemental iron that has been liquid and it's now solidified into little blobs. And when we clean it off, we see a few things here. We see that we've stuck molten iron to the reed heads. We've sort of started to delaminate the surface of this platter. That's a good thing. You know, we like that to happen. That makes us reasonably certain that we've exceeded the temperature we need to exceed to magnetically disorganize the disk. And we see we've actually welded the two platters together in this drive with a bunch of iron. But the rest of the platter looks pretty good, you know. So our 15 grams here, it's just not enough. So this is a fail. But I'm not ready to give up on Thermite yet, okay? Everyone tells me this is the stuff to use, right? Like, all these people can't be wrong. And the good thing about thermites is there's not just one of them. There's different kinds of thermite. The aluminum iron oxide one is the one that everyone knows and loves. But there, for example, is copper thermite. So this is aluminum and copper oxide. Once again, they swap their oxygen. If you would like to make it at home, It's 4.4 to 1, copper oxide to aluminum by weight. Copper thermite is a very aggressive thermite. So here's an unconfined little powder of it on a hard disk platter. And I'm just going to hit this with a torch. So that's not that kind of slow burn that we saw from the regular thermite. That's getting pretty close to like a flash powder or something. We could make firecrackers out of this stuff. So here we go. Here's our 15 grams of copper thermite pre-inserted into a drive. Let's see this. This is another high-speed shot. So keep watching this, because a few funny things happen. First of all, just to the right of frame, you can see the lid of the drive. It busted its screws out and flew away. But keep watching, because there's even more here. In just a little bit, when the smoke clears a little bit, we'll see what happened to the bottom of the drive. Oh, there it is. So it's done like a standing jump from that concrete block, right, into the air from the downforce of that explosion. This shot, by the way, as I said, I was doing it in my friend Miles Sledlip's workshop. It coated most of his workshop in copper. And we had to flee when we did this shot. This giant toxic cloud, came out, and we just ran outdoors, and his neighbors heard the explosion, and they were like, what was going on in there? And we was like, oh, no, nothing to worry about. Forget this like green smoke that's coming out the door. It's all under control. So you can see, made a really nice pattern on the drive, right? Nice artwork, all this like copper kind of bronzing. I recommend this technique if you make artwork. Just beautiful, right? We can take a look here. It's really gone all the way through the drive. No problem moving stuff around with this technique. And we can see that elemental copper has beaded up on the surface of the platters there. And even over the far side of the drive, we've got some nice little globs of molten copper that's gone on there. So if this was an electrical device that we were worried about, right? So not a magnetic storage system, but this was something where someone was going to have to try and attach probes and make it electrically function. This technique might be really good. There's like all kinds of connections now that it's going to be tough to deal with if you're reverse engineering a piece of hardware. But we're dealing with magnetic media here, not electric. So it's an electric device, but the magnetic part is the important part. So we wash it off, and the shiny coating's coming through. Not looking too good. And here we go with a close-up shot. We still got some copper stuck to it, even after we washed that drive. It looks cool, but I think people are still going to be able to magnetically recover forensic information from this drive. So infeasible, but fun. But I'm still not ready to give up on thermite, because everyone tells me it works. So let's really do this properly, industrially. Let's make a case that fits in 1U, attaches to a hard disk, and contains everything, and we can put a lot of thermite in it. So I made a mold out of a ceramic, and I molded it to a hard disk with a cavity in it, and we can fill up this cavity with a fair bit of thermite. We can get 250 grams of thermite in this, right? So we're like going an order of magnitude larger in mass. I built a wooden case to try and keep everything together. We got it all clamped down with clamps. Like, let's see how this goes. So far, so good. We're getting a little bit of containment failure here. But, this is really going to destroy some stuff. Incidentally, Miles Sledlip's workshop has a large, Persian rug on the floor of it, and this set most of the rug on fire. So sorry about that, Miles. But yeah, this we're dumping thermal energy into this drive. This is looking good. Once again, don't remember the frame rate, but this was shot with a Sony FX, so I'm guessing about 2,000 frames per second if you're trying to figure out the length of time that's happening here. All right, it seems like it's dying down. Let's take a look inside. So right away, we see some big globs of molten iron still there on top of the hard disk. And we see we've burned a hole through the top of the drive. So, you know, okay, life is good. Let's pull the lid off. And we see we've got all the drive electronics inside has got hot enough to completely melt and glob around. But the platters still look kind of okay. You know, like there's just, this thing is a big heat sink. So we've dumped a lot of heat into it, and that solid aluminum case has absorbed a lot of that heat. So I'm going to say this method could work, maybe, but I'm not going to rely on it if I run the data center and I really care about this data. So to me now, when someone says to me, Thermite is the way to destroy drives, I'm going to say, sure, you can do it, but you need a lot of it. So that's it for thermal. Let's move on to kinetic. And our goal with kinetic attacks is to deform, spindle, mutilate the drive material itself. And our goal here is to severely retard the use of any kind of mechanical system to scan the drive. You know, drives are very sensitive piece of electronics. Someone actually told me the other day, and I hadn't heard of this, that an ING data center had been doing a test of their fire suppression system. And the fire suppression system made so much noise, so much just loud vibration, that it vibrated the hard disk heads in their data center off their tracks, and their whole data center shut down because of this acoustic attack. It wasn't permanent damage, but just moving things a little bit off where they need to be makes it really hard to move to read the drive. So this is what we want to do. But if we care about really high capacity attackers here, we have to also use these techniques in conjunction with degaussing. All right? So just keep that in mind. You need to do your degaussing as well. But we're just going to look at the deformation of the drive here. And the things that I didn't look at, one thing I wanted to do was to build a horizontal hydraulic crusher. So you can buy these hard disk destroyers. Some of them mechanically operated. They're basically just an arbor press, and they have a big spike, and you pull down the handle and punch a hole through the drive vertically through the top. And I thought, well, that takes up more than 1U, but in our 1U rack, I didn't say anything about the sides. So you could make a horizontal one that pinches the drive from the side. You could definitely do it, but again, it's not so interesting because you know you could do it, so I didn't do it. I thought about using some other high-pressure cutting tools, like water jet cutters and stuff like that. Again, you can definitely do it. You know it works. Fitting it all into the space is tricky, and it's just not so interesting to do the research on because we know about it. But one thing that I really wanted to try was to punch holes in the drive, basically like shooting the drive, but not shooting it with a gun, because that doesn't fit in 1U, but with nail guns, which we could design a system that we could fit into our 1U plus our 1U above and below. So my first thought was, well, you can get these nail guns, which you use for putting nails into concrete. They're basically a little gun. They use a .22 caliber blank charge to fire the nail. Here it is going into Miles's concrete block, and we can see no problem at all going through a slab of concrete. That's probably going to go through a drive. This is 480 frames per second. It happens so fast, you don't even see the nail move. You just see the concrete explode. So let's see how it does on a hard disk. I got my spinning drive here. I milled off the end of the drive so that you can see inside and see what happens. Filming at the same frame rate, 480 frames per second, and bang, straight through, cracks that aluminum block case. I had to do the drive upside down because you have to hit this thing with a hammer to use it, and the top plate of the drive is kind of soft. So, this nail gun works. What I didn't think would work is a pneumatic nail gun, because I'm like, hasn't got explosives in it, so how good can it really be? But I thought I'd give it a try anyway. So here we go with our pneumatic nail gun, same drive because I already fired a nail through it, and at 480, wham, straight through, no problems at all. Color me surprised. I thought that was pretty cool. So in the interest of time, I won't show all the other videos, but you can see here we've totally gone through all those platters, and we've deformed them in terms of how the platter is now all wavy, and then also we've punched holes in it. So this is a feasible kinetic attack. We could easily fit this system into our rack according to the original rules. So that's great. This is sort of like the plasma cutter. We've sort of started off simple. But really the thing I was most excited about, and why I started this project really to begin with, is to investigate high explosive attacks. So with no doubt whatsoever, right, that we can destroy hard disks with high explosives. So we just know it, right? High explosives can destroy pretty much anything. And they also give you thermal factors for free because high explosives get really hot. So you can, for example, weld things together with high explosives, called high explosive welding. So this is great. But why is this interesting? Okay, I know what you're thinking right now. It's like, okay, come on. You said you weren't investigating things that you know that they work. Well, we have some things that we need to experiment with here. Number one, can we confine the explosion to the equipment? Can we do this without violating the rules? And then also, I personally wanted to experiment with new techniques. I've wanted to do this for years. So finally, this project made me put everything into place that I need to do this, which is 3D printing of high explosives. So this requires a little bit of academic explanation about what a high explosive penetrator is and how it works. So there's this effect in high explosives called the Monroe effect, and most people know it as what's called a shaped charge. And people who read about military stuff and anti-tank weapons and stuff like that, they've heard of this term shaped charge. And what it is a block of high explosive with a cavity in it. That's the shape. The shape is actually a hole in the high explosive. That shape is often conical. So if you have a circular thing, like for example, if you have an anti-ship missile, you want to punch a big hole through the side of that ship. That ship might have a foot of, 30 centimeters in European figures of steel that you have to punch through. So you have this big circular block of high explosive with a big hollow cone in it. But you can also make a linear shaped charge, right? So you can take a triangle and then cut it like a groove through your high explosive, usually in a line. So door breaching charges and stuff will use that. And what this cavity does is it concentrates the shock wave. When the high explosive explodes, it forms this shock wave that shoots out much more strongly and more directly than everywhere else around it. And that jet can cut through very, very thick material. And if you put a liner in there, which I'll show you in the next slide, you can form what's called an explosively formed penetrator. So the liner of the cone forms into a slug or a jet that increases the penetration dramatically. So here's a sort of schematic diagram of how that works. You have your metal liner up there in the cavity. It forms into a high temperature metal jet that greatly increases penetration. And so what you want out of your metal is to have a high density, so you've got a lot of kinetic energy behind that thing, and a high ductility, so it forms easily and gets really hot. So typically your liner of a shape charge will be made out of copper, or if you have a lot of budget, because you're a military organization, you might use tantalum. So here's an example of a commercial shape charge. These are downhole oil well perforators, right? So if you're in the oil and gas industry and you're drilling down and you want to get at the oil, the problem is if you just drill a big hole, it starts to fill up with oil, and it's messy and gross. And so what you do if you're drilling an oil well is you drill and you push pipe down with the drill, and at the bottom you have a sealed pipe, right? As soon as you reach depth, you push the sealed pipe down there and everything's sealed up so the oil is still sticking around. But then you want to get the oil. You want to slurp it up the hole. And so you send these things down there. These are designed to punch through inches of steel. These little tiny things. These are on my hand, so that's the scale. And these things just punch dramatic holes. So what they are is a block of very high velocity, high explosive, usually like HMX. They have a metal shell, and then they have a copper liner you can see on the right. At the top, there's a very sort of just thin piece of metal so that you put your blasting cap there or you put your deck cord there to set them off. And then some of them have a built-in standoff because sometimes you want a little distance to give that jet space to form. So here are a couple of oil-filled perforators that was given to me by the bomb squad from where I was doing this experimentation in Colorado. And what we have set up here, the red thing is the detonation cord that we're using to set off the perforators, and I have the perforators pointed up, right? So those jets are going to fire up in the air. So you just got a brief kind of glimpse there of what was happening. But let's freeze frame this and go to that frame where the explosion happens. So this is a very dramatic jet, right? High explosive goes in all directions, but the important part, it's going straight up. It looks like a laser beam. And this is an amazing shot, by the way. The fact, this is being filmed at 30 frames per second with a DSLR camera. To get this shot is extremely unpredictable because what we can see in here, over here, that's the kind of flame front from the blasting cap off frame that set off the det cord. The det cord itself, obviously it's set off the perforators, right? Because they're going. But the cord itself is still intact. So we've managed to, just out of sheer luck, capture this frame at just the precise moment when the perforators are firing, but there hasn't been enough time yet to blow apart the det cord. So you could try this, I don't know, probably 1,000 times and not get this shot. I was amazed that we got this. So here we go with a hard disk. This is just demonstration stuff because we know that this is going to work. This cuts through all kinds of stuff. So I have it strapped to the side of a hard disk. We're going to cut through those platters, and here's the shot. So, you know, it flew a little way, but we only had it strapped down with tape. Here we go with a little high-speed shot here. Not particularly high speed, but you know, from the FS. And you can see a little bit of drive sort of pop up there to the left, upper left. Easy to retrieve this afterwards and take a look at it. So here we can see just nicely cut through the side of the drive. Not the top, but the bottom cut through nicely. And here are the platters. They've popped off the spindle, but we've just chopped straight through them very nicely here. And here are all the bits of the drive that we found after that shot. But the sharp-eyed amongst you will say, hey, what's that? That wasn't there before. Let's take a closer look at it. Yeah, it's really a hole in our steel plate that we put down there. What about the other side? Okay, we've got a little exit wound on the other side. What's underneath it? Oh, there's a big hole. How deep does that hole go? Let's stick a wire in there. 15 inches. So again, in metric units, that is about 37 centimeters. So this presents a blast confinement challenge for our 3U rules here. We can't use one of these little devices. We're just going to totally punch holes in things. So let's get on to sort of the more interesting stuff from my perspective as a researcher. So I'd like to be able to design my own shape charges to order and do them in a CAD program, print them out, and I'll just be able to tweak the parameters and get them just right. So these are the parameters that I'd like to tweak of my shape charge, of course, total volume, but also the angle at the apex of that cone. The sharper the angle, the greater the penetration, typically. The standoff distance to allow the jet to form or not form completely if we don't want it to, and the total height of the charge, which is related also to just how much explosive we're using. And I would like to 3D print these, because 3D printing is cool. So it's easy for me to make models. These, in particular, are parametric models that I've designed in OpenSCAD, which for people who don't use a lot of CAD packages, I highly recommend OpenSCAD because it's the CAD program for hackers. You write code that defines solid geometries, and you can write functions that define geometries, so you can make parametric models really easily. But there's a problem with 3D printing stuff, right? Developing a new 3D printer for any kind of new material that you haven't printed before is a big materials handling problem, right? You've got to figure out how you're going to extrude that material, how you're going to deal with supports for overhangs and so on. You know, I want to print these cones, so there's going to be a void in there that I need to support. You want, especially with high explosives, you want this thing to be homogeneous. So just little tiny voids. If we're squirting out explosive out of a nozzle, for example, we could have all kinds of voids in there that are going to affect performance and make individual prints be unrepeatable. That's bad for science, and I don't want to have to deal with this. So instead, I'm going to do a shortcut. I'm going to print thin-walled enclosures out of a material that's very well understood. So I'm going to use a plastic printer to print a thin enclosure that's the right shape, and then fill it with an explosive that will self-compact and self-level. So I'll know that the explosive is exactly the shape of the interior of that 3D printed enclosure. And as far as I'm aware, feel free to come up and tell me anything else because I'm interested in this stuff. This work here that I'm presenting to you is the first open literature 3D printing of high explosives. So I'm sure that there's been military classified experiments into this, but I don't know of anyone else in the civilian community doing it yet. So let's look at the explosive that I'm going to use. I'm going to call it Felix. which I say stands for Field Expedient Liquid Explosive. And I say I'm going to call it because what I did here is I found a commercial product that's a liquid high explosive, but it's expensive, and I'm a hacker, and I'm cheap. I don't want to have to pay commercial product prices. So instead, I reverse engineered it. And I looked up the original patents, and I figured out how to make it, and made my own. So I call it Felix. And it's similar to a kind of explosive that surprisingly, or maybe not surprisingly to people in Europe, you can just buy in the United States. You don't have to have any license for it, called Tannerite. And the reason why you can just buy it is because this is the explosive that people who shoot guns like to make into targets so that when they shoot their target, it explodes. And in America, you're allowed to have guns. So, of course, if you're allowed to have guns, you're allowed to have exploding targets, because why not? And the reason why you can have this stuff is it's very hard to set it off. You need to hit it quite hard. And it's only legal to set this stuff off with a bullet. So that's how the law is written. So you can buy this, but you're not allowed to just play with it and set it off with blasting caps and stuff without licenses. You have to shoot it with a rifle. And it's based on ammonium nitrate, which is a high explosive, but it's very insensitive. And so it has aluminum powder in there to sensitize it. I want to use not a powdered explosive like Tannerite. I want to use a liquid. So mine is based on nitromethane, which you might know as racing fuel for high-performance race cars or model aircraft fuel. Again, you can buy that on Amazon. And the sensitizing agent is also aluminum, but because it's a liquid, it has to be a kind of a special aluminum. So you need a particular particle size, 5 to 50 microns, and then you need to coat it with stearic acid. That's very, very important. It doesn't work. I tested it. I tested it with other aluminum powders. It only works if you stearic acid coat it with 1 to 2%. This stuff is great because these two parts, the aluminum powder and the nitromethane, they're both a hazmat shipping item, but they're not a high explosive until they're mixed. So once again, you can order these over the internet. They'll be shipped to you. You have to pay a little extra for the hazmat shipping charge, but no license is required. Once you mix it together, then you got to have the licenses. And we got all the licenses we needed for this work, because the last thing I want to see is the inside of an American prison. So here's the stoichiometry. The nitromethane, it's an explosive by itself. It decomposes into various gases and water, but very, very hard to set off. The aluminum powder sensitizes it, and it also adds energy. So we can see the water that's produced by that decomposition of nitromethane reacts with the aluminum and produces more gas, more heat. That's how it works. So first of all, I thought, let's do a linear shape charge that we wrap into a ring. So we've got an annular shape charge. There's the OpenSCAD model. And here we go with 3D printed versions. It all fits into one U. According to our rules, we can put 60 grams of Felix into it. That's what it looks like. It's like a nice little silver slurry. There we are, all set up for a disc shot. So let's see how that goes. Bang. This doesn't even go very far. Very nice. That's what we like to see. Here we go with a high-speed shot. So, you know, this blast confinement challenge, but we're getting there. Here's another shot just for fun. Same design, a smaller standoff, that's all. That one, the drive does fly out of frame. And you can see this here in the high speed. Off to the left, the right. And let's take a look at what we got here. So we can see a few things here. Number one, we can see that my mixture, this was with a stoichiometric mix, right? Because I'm still reverse engineering the explosive. So even though it's exactly what's needed for the reaction if it was confined, we've got a lot of aluminum coating the drive now. So we don't need to use that much aluminum. The stoichiometric mix is not the optimum mix for this. Secondly, we've stripped the platters off the spindle. So that charge really has generated a lot of downforce, and it's pushed those off. And we have generated a little bit of a cutting jet here, okay? So we've cut through the drive there. And sorry, I did these arrows out of order. But on the left, we can see we've cut through the drive a little bit, but not all the way around like we wanted to. And why not? Well, my theory is that corresponds to where the blasting cap is, right? So it's done the right thing, right where we initiated it, but hasn't gone around the circle. And then on the right, that's an example of explosive welding, and you'll see that again in a little bit. So different different design. Let's try a radial shape charge. We're going to initiate this and try and cut this thing into chunks. There's the OpenSCAD model. I've made a lid for it with a little hole to insert the initiator. And what I'm going to initiate it with, this time a little more Felix, and I'm going to initiate it with det cord. So we're going to hit it all the way around at once to set it off. There we are, all wrapped up. And let's take a look. All right, things really moved there. Let's take a look at the high-speed shot. This is a little shy of 1,000 frames per second here with the Sony FS. So, okay, once again, blast confinement challenge, big fireball, but we'll get to that. All right, that's just the smoke clearing. Here we go with a wide shot. So this time you can see where the bits of that drive goes. They move really fast, even at 120 frames per second. So these are the bits that we could find of that drive. The circuit board, as you can see, almost all of the components have been blasted off the circuit board. Here is the top of the drive and part of the platters. There's a close-up of the platters, and you can see that we've definitely cut it in a bunch of places, and we've also high explosively welded the platters together. So, great. But you're still saying, all right, you asshole, you said that there were these rules that you were trying to follow, and you weren't interested in doing stuff that definitely works regardless of the rules. So come on. All right. So, blast suppression. We need to couple this shockwave from the explosive to the drive, right? We need to bust that drive. But we don't want to couple the blast to our equipment. We want our equipment to survive. So we have our explosive against the hard disk. We need some kind of damping material in between the explosive and the equipment shell so that we're protecting everything else in our data center. And here's what we want out of a damping material. It's got to be some kind of matrix that alternates stuff that compresses and stuff that doesn't compress so that we can absorb that shockwave and break it up as it's going to the equipment. So an ideal material would be some kind of a foam that's a mixture of a liquid that doesn't compress and a gas that does. So a little bubbly liquid foam. We want it to not cost a lot because, again, we're cheap. And we want to be able to inject this when we need to because we don't want to have our data storage equipment totally full of this liquid all the time. Well, what kind of magical material can we find that has all of these properties and doesn't cost very much? It turns out good old supermarket shaving cream is amazing. And I learned this from an explosive engineering instructor. He said, well, we do these demos in class where we punch out lock cylinders. And we can't have things like flying around and hitting the students. So we put a big cup full of shaving cream over the top of it. And you'll be surprised. OK, let's have a look. So here's a whole bunch of det cord on a drive, plus shaving cream, in a box. This is a big blast, right? So we're trying to see what can we get out of this, right? This is just an experiment. I'm not using the Felix this time. So here's the video in real time. So we could already see here, it's not this dramatic explosion that we just saw before, right? But this is a bigger explosion than what we did before in terms of how much high explosive is there. So let's look at some freeze frames. This is the first frame of the explosion from both cameras. We had two cameras pointed at this. This on the left is the damped explosion. And it has 2.5 times as much explosive as the one on the right, undamped. First frame, camera 1. This is the closer camera. In the top frame, you can see it in its protective box. There's first frame damped, first frame undamped. So this shaving cream looks like it's really done something here. So let's do it with the stuff that we're testing. So we've got our radial shape charge, 75 grams of Felix. We've made a little simulator of our 1U data storage rack out of some steel. And we've put our drive there. We put in a blasting cap, spray it down with some shaving cream, and then to simulate we get 1U above the thing, right? So this isn't 1U, but it's like imagine we put 1U of concrete above this, right? So we've got a bag of sand simulating our concrete on top of a steel plate. I think this is fair to represent 1U. So let's take a look at it. So, you know, we're still, some stuff is moving around, but we've dramatically reduced the amount of sort of collateral damage we get from this blast just with a can of shaving cream. There's the high-speed shot. See, things do fly up in the air, so you have to build this pretty heavily reinforced. But I think things are looking good experimentally, right? Pending future, like, serious engineering effort. Take a look at our steel plate. It's made a dent in the steel plate, but that dent is actually pretty small compared to these dents here from earlier shots. These are earlier test shots where we had film canisters full of Felix when I was figuring out the Felix formula. Our rack hasn't survived super well. The steel irons, the angle iron pieces have flattened out, so you know, that's not great. And we can see we've made like an imprint of the hard disk on that steel plate. But it doesn't look like the kind of situation which is impossible for us as engineers to figure out how we could do this in a data center environment. So my conclusion on this, with some more engineering effort, it just might work. So moving on quickly to electric. I'm sorry that I'm going long. So everyone, if you're really hungry, you have my permission to run out and get lunch. But also feel free to stay. I'm just going to go through this stuff because I think it's fun. Our goal here with electric attacks is to use the thing that we already have in abundance in our equipment against the media, and that's electricity. We've got power. In particular, here's where we look at SSDs, right? Because I think we can use electrics against this. So again, things I didn't look at. Number one, degaussing. We know it works for magnetic media. Doesn't work against SSDs. EMP, microwaves, RF attacks. Leave that for another time. So number one, we're still going to be like, this is kind of mix of electrics and kinetics here, right? So can we use a wire that we pump so much power through that it physically explodes and use that against chips? So you can make a exploding bridge wire that will set off high explosives. They're used in atomic weapons. So here's our exploding bridge wire rig. It's kind of janky, as you can see, but obviously could be scaled down. And this is where I'm very thankful to conference swag, because I don't want to buy a bunch of really expensive SSDs and blow them up, but they're just flash chips on a circuit board. So instead, at a conference, I harvested a whole bunch of those free flash drives to do my attacks against. So thanks, MathWorks. Here's the exploding bridge wire rig, just to give you an example of what it does. We've got our wire stretched across our two terminals here. And here's what happens.
2, 1.
That whole wire just explodes in an instant. So that's not just burning out a fuse here. This is pretty serious. Here's a high-speed shot with the FS, 960 frames per second. To show you, this basically happens, to all intents and purposes, instantaneously. So what are we going to do with this? Number one, okay, let's say we don't want to seriously mess with our storage media, but we want to just install something. So can we just wrap this around the outside and physically attack our circuit board
3,
with the exploding
2,
bridge wire?
1.
So here's a high-speed shot of that. So this is not a long, big kinetic energy push. This is a sharp impulse that we're hitting this with. What does it do? Well, we can already see from the high-speed shot, it doesn't do a whole hell of a lot to the flash chip. However, it does decap the processor on the other side. So we're applying some force here. It's just not really enough. So this method is unreliable. But we're just getting started here. What would be nice, and I did this before the recent USB kill drives and stuff like that. I did this electric work early last year. What about if we can raise the level of the ground to be a high voltage power spike? We raise the ground instead of raising the power, because a lot of devices have protection against power spikes. They don't usually have protection against ground spikes. So I've modified our drives with a little tap here that's going to go to our exploding wire system. And here we go in real time.
3, 2,
snap. And here's a 960 frames per second high-speed shot. And we can already see something's happened to that drive. And what has happened is that the exploding wire, this time, wasn't a wire across our terminals, it was the wires on the circuit board itself that exploded. So they've all delaminated off the circuit board and physically punched the chip off. There's the flash chip. We've split it in half and we've decapped it. So high voltage power spike looks like we can do a lot of damage to a chip here, right? So forensic resistance of SSD chips, still not fully known. But what's clear is that you're not going to electrically connect that chip up again and try and read that data back out of it. Any kind of potential attack on the data on there is going to have to use electron microscopy. Even then, it might not work. It probably won't work because I'm not sure how visible storage on flash RAM is. I don't think that it is. So finalizing the electric attacks, this is some stuff that I shot a little earlier before this research, and I would love to do this on a real drive. I ran out of time, but I wanted to show it to you guys because it's freaking cool. Not too many people have seen this. This is inductive deformation. So the idea is we have our coil, we dump a huge pulse into it, and it creates a giant changing magnetic field, just like in a transformer, but it's just a huge spike. And so that induces a reverse magnetic field in the stuff inside. So the coil is going to repel the stuff that's in the middle. The coil is going to move outwards. The stuff inside is going to move inwards. If it's aluminum, it's a great substrate for doing this. So here I'm going to do it on a can, but imagine there's a hard disk in this coil. This is a shot at 2,000 frames per second. So spooky action at a distance here. We're not physically crushing this with the coil. The coil is moving the other direction. It's the magnetic field that's punching this can in and ripping it in half. Here's another high-speed shot, a medium-speed shot at 2,000 frames per second, different can. And so you can see the coil overcomes the zip ties and goes crazy, but it never touches the can. That's not what's causing the crushing here. But we can, and here where I mentioned we're going to go faster than what I showed before, here we can go really fast. We had some very good cameras for this shoot. This is 2 shots at 100,000 frames per second. So here on the left, we see even at 100,000 frames per second, this happens very, very, very fast. Here on the right, same deal. So the sparks from the switch closing, right, take longer to come out than the can takes to crush. So the whole time that I've been talking over this particular slide, 10 milliseconds have not yet elapsed. So super cool. I totally recommend playing with high voltages. Just be careful. Keep one hand in your pocket. If we, were a research lab or someone that really, really cared about this, you could crush a hard disk with this. But the necessary power levels to scale up from a soda can to a hard disk, unknown to me. We could do some engineering calculations, we could figure it out. But you're going to need a big power supply to do this. Not a trivial engineering challenge. So here's a summary of everything I investigated. Of the most feasible methods, right? So if you want to set up an instantly self-destructing data center, here's my recommendations. In the thermal category, plasma cutter was great. Low tech, sometimes beats everything. And the oxygen injection, I think is feasible, but you might need a complex injector mechanism, right? You might need to inject from multiple places because the drive is going to be burning up. Kinetic, nail guns are great. So if you're not going up against the NSA, you can just fire a bunch of nails through it, and you're probably going to be fine. And the damped high explosive. Yes. Yeah, we're glad to hear about that because we like high explosives. But you're going to need to pay attention to the sides as well as up and down. And then electric. High voltage power spike. Works great, but still, if anyone knows someone that does like hardcore, like military grade forensics and knows about what they do to forensically recover stuff from SSDs, have them come and talk to me if they're willing to share any of that information, because I'd love to know just how much you have to destroy a flash chip to make sure that, I'm just kind of operating under the assumption that as long as the chip is completely unusable, you're probably okay, but you know, maybe I should talk to Travis about it, he probably knows. So just to leave you with something, after I did this work, I was talking to some Navy guys from SPAWAR, and they were like, oh yeah, like I worked on one of those projects once, because we had drones, and we wanted to make sure that if the drone ever crashed and a hostile person got hold of that drone, they can't recover anything from its classified systems. And he's like, yeah, we did some explosives, you know, a few years ago. Can't tell you much about it. So I thought, okay, well, what about the case of the mobile device? You know, you've got something with you, and some criminal comes and takes it from you, right? So like, you know, the Iranians, they capture a drone. You want to get rid of that hard disk, or you personally, you know, you've got your laptop, you got a lot of stuff in it, and what if someone steals your laptop, you know, and what if it's on when you're using it? So you haven't had time to lock it, so your full disk encryption is worthless to you. But it's pretty easy to make a little smartwatch or a little dongle in your pocket that communicates over Bluetooth low energy, and it determines when it gets out of range. So these people, they carry off your unlocked laptop, they get out of range, and, well, what happens? So incidentally, the amount of explosive in that laptop for that shot was about this much det cord. You know, like 2 inches. Fit quite nicely in the CD-ROM bay of that MacBook Pro, which made me sad to blow up a Mac. But the moral of that story is stop wasting my fucking time at the airport, right? Like, making me turn my laptop on does not mean anything. Thank you very much. I'll be totally happy to answer any and all questions over lunch. And thanks for sticking with me as I ran over time.